So last we spoke, we found that the perihelion velocity, we're in an elliptical orbit, perihelion velocity, really the speed, really speed, astrophysicists using speed and velocity despite how we call pressure all the time. Speed and velocity are different things because speed is just the magnitude of velocity vector. And we say escape velocity. Same speed, sorry. The perihelion speed, sloppily called velocity, Vp squared is g times the total mass, the sum of the two masses, times 1 plus the eccentricity of their elliptic orbits about one another, which is the same as the eccentricity of the relative orbit in the equivalent one-body problem, divided by the perihelion distance, which turns into g times m over a times 1 plus e over 1 minus e. And then similarly, the aphelion velocity squared is gm over a 1 minus e over 1 plus e. So you just flip the term in parentheses between the two of them. And now we're on to the next glorious discovery to see what the total orbital energy is. Of course, it's conserved, so can we find a nice, simple expression for it? No, I'm just going to waste some time showing. No, we can find a nice, simple expression for it. The total orbital energy is, someday I should just be like, punk everybody. It's like, go through this long thing. It's like, oh, unfortunately this doesn't work, and then just keep going or something. Probably better ways to spend time, but I don't know. Anyway, so total orbital energy, remember that's the sum of the kinetic and potential energy, and in the equivalent one-body problem, we get the right result for the two-body problem by treating everything as belonging to the reduced mass, so you get its kinetic energy, 1/2 mu v squared, and the orbital energy is constant, so let's just plug in for the perihelion distance. Doesn't matter where it is in the orbit, but it's certainly true everywhere, so it's true at the perihelion distance. So it's 1/2 mu v squared minus g m mu over r perihelion. I could put v sub a over r sub a. I could take the subscripts off. Subscripts off, because this is true at all times, no matter where you are in the orbit. But let's do it at the perihelion distance because it gives us something nice. So that's the total orbital energy, the conserved orbital energy. So let's use what we know about Vp squared and Rp. That'll be 1/2 mu Vp squared is given up there. Gma over 1 times 1 plus e over 1 minus e. Gm over a times 1 plus e over 1 minus e. And then we know that the perihelion distance, remember that, is a times 1 minus e. What's the aphelion distance? Instead of a times 1 minus e, it's a times 1 plus e. So you do this also using RA, using that other substitution. And then the 1 plus e over 1 minus e will flip over, but we're doing it for perihelion, so let's stick with it. Minus gm mu, we're going to get the same result either way, minus gm mu over a times minus e. Oh my gosh, there's gm mu's over a's everywhere. So let's pull that out, along with the 2 just to boot. So factor this as gm mu over 2a times the quantity. So we've got 1 plus e over 1 minus e, 1 plus e over 1 minus e, minus, so I'm going to need a 2 here because there wasn't a 1/2 on this, so the 2's will cancel with this factor here, 1/2, so, I'm sorry, this term doesn't have a 2 in it, so I have a 2 out here, I'll put a 2 up there to compensate for it, minus 2 over 1 minus e. Ooh, common denominator. Common denominator, so this is gm over 2a, and so we get 1 plus e minus 2 is the same thing as e minus 1 over 1 minus e. But what's e minus 1 over 1 minus e? Now I'm looking for a real simple result here. What is e minus 1 over 1 minus e? What if I wrote that? E minus 1 is the same thing as minus 1 minus e. So I ask again, what is e minus 1 over 1 minus e? It's just minus 1, yeah. So this just becomes, in the end, minus 2 gmu over 2a. And that cancels too. So minus gmu, no, it is 2a, yeah. There was no 2 there. Minus gmu over 2a. So let's put it back next to that e and say, ooh, box where e is equal to minus g m mu over 2a, but remember that m mu, what's m equal to in terms of m1 and m2? m1 plus m2 is the total mass, so that's m1 plus m2, the two actual masses that are orbiting their common center of mass. And what's the definition of mu? Stand on your head and say it again.
Huh?
Stand on your head and say it again.
Oh, m1 times m2 over m1.
Yes, that's exactly what you meant to say. Yes. Right? So in other words, keep that in mind as just like knee jerk. M mu is the same thing as m1 and m2. Those two things are equal to one another. So equals minus g m1 m2 over a is the orbital energy, the conserved orbital energy over 2a. Stop it. Over 2a, the conserved orbital energy. So, notice, big deal. E depends only on A, and therefore, and not on E. It doesn't depend on the eccentricity. All it cares about is the semi-major axis for a given pair of masses. Only thing that matters is the semi-major axis. The shape of the orbit doesn't matter. All that matters is the semi-major axis. So, here's a circular orbit. Here is an elliptical orbit. Compare the semi-major axes for those two orbits. Same or different? Different. So if I wanted to draw the semi-major axis for this ellipse, starting from its center, what would I do? go to either end, right? I go to either end. The semi-major axis is half the long axis of the ellipse. Yes?
If it was an ellipse like that, wouldn't the center mass have to be more to the left or right?
I'm not claiming that the center of mass is in the middle. I'm not claiming that. I'm just saying, here's two orbital shapes. Yeah, for this one, there's like a focus over here. For the circle, focus is in the center. So I'm not claiming anything about where the center of mass is or anything like that. I'm just saying, here's two orbits. One's a circle, one's an ellipse. So here is the semi-major axis of that ellipse. How does that compare to the radius of the circle? It's the same thing. And how is the semi-major axis, how do you, from the radius of a circle, how do you find its semi-major axis?
Its radius.
It is its radius, right? For a circle, the semi-major axis is the radius. Well, every radius is the semi-major axis for a circle, right? So, in other words, keep that in mind, I can draw a whole family of ellipses, right, that have the same major axis and therefore semi-major axis, all the way up to when I get it to be a circle. And ultimately, you can even, skinny, 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 till you finally degenerate into a straight line, right? All these orbits have the same value of A. So a pair of masses, a pair of given masses, we know M1 and M2, that keeps staying the same. A pair of given masses with any of these orbits, and really it's an infinity, right? Any ellipse all the way out to opening up to the circle, all have the same total orbital, what's the last word? Energy is what I'm looking for here. And you're right, we do have the same periods because the period just depends on, A, right? So you're right, but it's not what I was looking for here because we're talking about So they all have the same orbital energy because it only depends on A. It only depends on A, and those all have the same value of A. So they all have the same orbital energy. Where the center of mass isn't the same for all of them, but that's not the point. It's just they all have the same orbital energy. It's only the length of the major axis matters, not the shape of the orbit. Where by the shape we mean its eccentricity, how squishy it is, so to speak. Okay? Ooh. But wait, there's more. Note that from L is equal to mu times the square root of GM A times 1 minus E squared. Right, that was our formula for the orbital angular momentum in terms of the masses, which would allow you to find mu in capital M, and the semi-major axis and the eccentricity. Right? The orbital angular momentum depends not only on the semi-major axis, but also on the eccentricity. For a given value of A, and thus E, given value A, and thus the orbital energy E, the maximum value of L, the maximum value of L corresponds to a circular orbit. Because if E is 0, this is bigger than it would be for any other value of E, because it's 1 minus E squared under there. Corresponds to a circular orbit. So all these orbits have exactly the same energy, but the circular one has the largest orbital angular momentum. The other ones have smaller and smaller orbital angular momenta. Down to 0 if the eccentricity is 0, because that would be the case where they're just, well, they would collide. If you ignore that fact, they're just moving back and forth along a straight line. And in that case, if you're finding the orbital angular momentum with respect to the center of mass, then the orbital angular momentum is 0, right? Because the orbital angular momentum is r cross p, but if it's moving along a straight line and you have the origin on that line, then p and r are in the same direction, so r cross p would be 0. So that would be 0, as predicted, orbital angular momentum for a straight line orbit. And the more you move away from that, the more orbital angular momentum you get, up to the limit of the circular orbit with that given value of the semi major axis. Yes, indeed. Indeed. I think that's a pretty nifty result. I said, suddenly it was 1955 in here. That's really nifty. But, Dan, Helmut, that's really nifty, isn't it? Solving this expression for A, we obtain A, this expression over here, solve that for A. A is equal to L squared over GM mu squared times 1 minus E squared. So we can turn things on its end from what we said there, because what this says is for a given L, so instead of fixing the energy, let's fix the orbital angular momentum. For a given L, A is a minimum when, so what value of E will make A as small as possible? Remember, E goes between 0 and 1. What value of E will make A as small as possible? It would be 0, yeah, because if I make E bigger than 0, this term gets bigger, we're dividing by it, so the result gets smaller. So A is a minimum when E is equal to 0, which implies that, and I'll explicitly say it again, for a given L, for a given orbital angular momentum, E is a minimum. E is a minimum. Minimum. Oh, sorry, I didn't say it right. A is a, well, no, I was going to say minimum, but I should say E is a minimum. I.e., so in a sense I said that, but what it really means is most negative. In terms of biggitude, I can say really, yeah, E is a minimum. but since it's negative, I should color it different. E is a, yeah, that's like a big negative thing, right? E is a most negative for a, you got it, circular orbit. Oh, sorry, circular orbit. Right? Gotta keep going. Circular orbit. So, in other words, kind of goes, similar ways here. That you get the maximum L for a circular orbit for a given E, and for a given L, you get the minimum E for a circular orbit. Most negative E, because it's minus G M1, M2 over 2A. And so the smaller A is, the more negative E is, and therefore the smaller E is. But remembering that with negative numbers, smaller means bigger in magnitude, right? Because of algebra, right? So for a circular orbit, of course we must not forget. Ooh, ah. And this has some nice applications. This fact has some nice applications.
Looks like a big juicy watermelon.
It does, doesn't it? Yes. Yep. Could be that. It's kind of also maybe a basketball on some level. That's a watermelon. Okay. We'll go with the watermelon.
That's my favorite food.
Oh, okay. Well, there you go. All right. Yes. So next time you see a big juicy watermelon, just remember that result of Morgan campus.
Right, the size of you doesn't matter.
Exactly. That's right. In terms of the end. Now, in terms of stuff. Right? It matters for when you're looking at the orbital. Okay. So application. Application. Some applications here. Orbits in a close binary star system in other words, the two stars are close together. Their separation is not particularly large compared to their radii. Tend to circularize over time. So a close binary star system, they're close enough to one another that they can even distort their shapes because of tidal forces, and so they can develop teardrop shapes towards one another. Yes?
Is there a threshold E value beyond which they would tend to circularize?
It's really more about how close they are to one another, and really any binary system, the orbits will tend to circularize. It's really a matter of how long it would take the orbit to become circular. And if their separation is far apart compared to their radii, the answer is longer than the age of the universe. Whereas if their separation is comparable to the radii, it happens on kind of reasonable timescales, so to speak. But there's no particular number. In other words, it's a gradual transition. The closer they are, the faster this happens. So yeah, so basically, essentially, if their separation isn't that large compared to their diameters, then this is going to happen in a pretty fast timescale, astronomically speaking. Right? I mean, you're not going to want to make popcorn and watch it. But on the other hand, astronomically speaking, it's not that long. So, why? Tidal friction. So they get distorted shapes, and that means that as they're rotating internally, you get friction between different layers because of that distortion. Tidal friction dissipates orbital energy you can turn orbital energy into heat and radiation. They can get rid of orbital energy that is radiated away. But for a closed system, and you know, if there's no other stars nearby, they're effectively a closed system. They're not interacting with anything else significantly. For a closed system, there's no way to dissipate orbital angular momentum. You can't give that to anything else. You cannot dissipate their angular momentum. Can't turn that into radiation. So over time, the orbital shape, the relative orbit, and thus the individual orbits, moves closer and closer to the minimum configuration. What's the minimum energy configuration? I mean, sorry, I said to the minimum, the minimum, the minimum, right, what I'm trying to say is, okay, gotta think about it here, right, so they're keeping the same orbital angular momentum, right. So they're going to move to the condition of E being the minimum it can get to, which would be what? Circular. A circle, a circle, a circle. At which point there's not going to be dissipation anymore. They'll just be happily orbiting one another in a circle. And in fact, they also, because of this tidal friction, they tend to get to the point where their rotation and their orbital motion are synchronized. In other words, it's like happens with the moon orbiting the Earth, right? You know, the moon keeps the same face towards the Earth at all times. You all know that? Are you familiar with that, right? So that if somebody in the middle of the room is the Earth, is the moon, sorry, is the Earth, here on the Earth, the moon, and it's like, I cannot take my eyes off of that beautiful planet. I just cannot. And so the moon's orbital period and its rotation period are the same as one another. Now, the moon has an elliptical orbit, so it's not perfect, and so we see the moon nodding back and forth in what we call libration. But over time, if you wait long enough, the moon and Earth will evolve to circular orbits, and they'll both be locked. The moon and the Earth will both keep their faces towards one another as they do-si-do. The sun will become a red giant before that happens, but if you waited long enough and, you know, like, stop it, sun, stop it, then eventually they would get to that configuration. What questions do you have? Yes?
What is the difference between a closed system and an isolated system?
That's the same thing.
Really?
Yeah, it means the same thing.
Okay.
Yep. So there ain't no difference.
Understand.
Yes. Yep. It's just a way of saying it's not interacting with anything else. Which, of course, there's not such thing as a truly closed system. I mean, you're still interacting with the rest of the universe, but, you know, okay, the star Antares isn't having a big effect on my life, and what? Oh, hello, Antares, so beautiful. You're not Mars. But at the same time, gravitationally speaking, in terms of the radiation, not doing a lot to affect my physics that way, so to speak. So really, there's no such thing as a closed system, but it's a good approximation in many situations. Yep. I did see once, so you know, there's like a chaotic dynamical system. So small changes in initial conditions can, in many circumstances, grow to very observable effects in a short amount of time. So an example is, is a triple pendulum. If you have a pendulum attached to another pendulum, so there's multiple dots like that, or a double pendulum, that's a chaotic system. Just you will never be able to swing it and have it do the same motion twice. If you watch for not very long, you try to start it exactly the same way, and after not very long, the motion will be very visibly different between them. Because it's a chaotic system. Unlike a regular pendulum, a single pendulum was very irregular, it's easy to predict what it's going to do. Even simple systems can exhibit this kind of chaotic behavior. I was at a museum in West Virginia once, where they said something that's very true, it's a very good point. They had a double pendulum, and they pointed out that your thoughts were visibly affecting its motion, because your thoughts are associated with weak little electromagnetic waves, and even tiny forces like that are causing tiny perturbations in the motion that rapidly get amplified to visible differences in how it's moving. Not that you can control its motion with your thoughts. You can't say, I want it to be over here at this time. But nevertheless, your thoughts are affecting its motion. And I also once read in Scientific American, I haven't checked it, but I mean, the authors said it, so it has to be true. It probably is. Imagine a game of billiards. You take out the pockets so that none of the balls ever leave. So it's perfect billiard table, perfect ideal billiard table. They're frictionless. So you hit the balls with the cue ball, and then you just bounce around forever and ever and ever. The claim was, if you neglect the gravitational influence of one electron on the other side of the galaxy, you would be able to notice the difference in the motion after about 1 minute of those balls in that case. So when they say that it's really sensitive to perturbations, to any change in the initial conditions, they mean it. It's incredible, right? Just how sensitive things can be to that sort of thing. And you all heard of the butterfly effect before, right? This is why weather forecasting will never be perfect. It's just impossible. It's not that forecasters are not smart enough to come up with better models and so forth. It's that the weather is a chaotic dynamical system, and it's absolutely impossible to predict it with perfect accuracy. Even if the universe were deterministic instead of quantum mechanical, you would have to know the positions and the momenta of every particle with infinite precision, literally infinite precision, to be able to forecast the weather reliably into the future. And so even small errors lead to larger and larger errors over time, such that we can, it's good enough that we can get kind of general trends, but you're never going to be able to say exactly what's going to happen in like 2 months from now. It's just impossible. It just requires impossible precision. It is, yes, it's crazy, yes. Okay, here's another one, a similar one. So Neptune has a moon called Triton. Planet Neptune has a moon called Triton, which is in this long elliptical orbit. And it's in fact, it orbits retrograde. And so it was captured from the Kuiper Belt. Triton is basically a very Pluto-like world that, like Pluto, used to be part of the Kuiper Belt of bodies out there, large cometary bodies. Some of them just would be comets that would come to Earth, but there's also, Pluto's like a giant overgrown comet nucleus, basically. So is Triton. You can't, so orbital capture like that is tricky, because if you think about it, if something's coming in on a hyperbolic orbit, it's got enough energy to never come back again. Well, if you conserve orbital energy, you can't capture something because it'll just fly off again. If it's not in orbit to begin with, if it's on an open orbit to begin with, it's still on an open orbit at all times, and you cannot capture it. The only way you can have orbital capture Mars captured its 2 moons, Phobos and Deimos. Neptune captured Triton. Jupiter has captured asteroids and so forth. Is for there to be a dissipative mechanism. In other words, while Triton was on its way to Neptune, when they were approaching one another, it raised tides on Neptune and vice versa that dissipated a little orbital energy by friction and allowed the total orbital energy to become small enough that it switched to a closed orbit. So Triton was now a closed orbit around Neptune. That orbit would have been more eccentric initially because tidal friction has now been making the orbit evolve towards circularity. And so we can say another example is Triton's orbit around Neptune was probably once more eccentric. And it's still rather eccentric, but it used to be eccentricer, which isn't the actual word. Okay. Questions, comments, observations? Yes?
Are you only able to have tidal friction if there's like fluids involved?
Yeah, so it doesn't have to be literally a fluid. So in other words, solid bodies can never be perfectly rigid. So if you had an ideal rigid body, it's undeformable, then you wouldn't have tidal friction. To have tidal friction, you need the body to be deformable. But that's everything. In other words, there's no such thing as a perfectly rigid body. But it's easier on a fluid planet than it is on a solid planet. But even Earth, even the solid body of Earth has tides from the moon. It's just that they're on the order of like an inch a day instead of feet per day is what it comes down to. Now, there's a nice proof that you can't have a perfectly rigid body involving relativity. So if you took 280 from me, I would mention it to you. I don't know if Dr. Dingley mentioned this. But how do we know you can never have a perfectly rigid body? Simple thought experiment. Here is a rod. Here's the sun. Well, here's Earth on one end. Here's Alpha Centauri on the other end. And I smack one end of the rod. If it's perfectly rigid, if it can't deform, as soon as I smack it, the whole thing moves. But that means I could send a message to Alpha Centauri, like in Morse code. I could say, and that message would instantly reach Alpha Centauri, because as soon as I poked one end of the rod, the person on Alpha Centauri would be like, poke, 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 right? So I would have transferred information at infinite speed. It got there instantaneously. A rigid body would allow you to transmit a signal at infinite speed because no matter how long it was, if it's truly rigid, if it can't deform, as soon as you touch one end, the effect immediately shows up on the other end. That would violate relativity. And so rigid bodies can't exist if relativity is true. Yeah, we have a lot of evidence relativity is true. So therefore, rigid bodies cannot exist. Violate relativity. Cute, huh? Ah, cute. All right. Let's see. Okay. For a circular orbit, E is minus G, M1, M2, over 2A, but A is R, so it's over 2R, the radius of the orbit. While the gravitational potential energy is minus G M1 M2 over R, right? Because that's just the formula for the gravitational potential energy. And we now know that the total orbital energy is always minus g m1 m2 over 2a, but for a circular orbit, r is a. So the total energy is minus g m1 m2 over 2r. The potential energy is minus g m1 m2 over r. Why compare those two to one another? Is there a very simple relation between them? Yes, right? So E is equal to minus 1/2 U. The total energy is minus 1/2 the potential energy. Minus half the potential energy. So that means that the kinetic energy is making up that difference, but the total energy is negative, and remember we said bound orbits have negative energy. They've got, if you let the gravitational potential energy be 0 to infinity for a bound orbit, the total energy is negative because the positive kinetic energy is smaller than the negative potential energy. So for a circular orbit, that simple case, E is minus 1/2 U. For an elliptical orbit, by doing problem 2.9, you will joyfully show, it's always joyful, you will joyfully show that in fact, the time average gravitational potential energy time averaged over one orbit, time averaged over one orbit, time average over one orbit of U, the gravitational potential energy. So it's changing with time because the separation between the masses is changing. So instantaneously, it's minus gm1 m2 over r as a function of time. It's constantly changing, but we can take the average over one orbit. You will show that that is in fact equal to minus g m1 m2 over the semi-major axis, so that the circular orbit is just a special case of this one. You've got the semi-major axis is the radius of the circle. So that we can say that the constant energy minus g m1 m2 over 2a, so it's always minus g m1 m2 over 2a, and its constant is in fact equal to 1/2. Okay, what's wrong with my statement right here? That E is minus 1/2. Did you catch it? Did I say that? Yeah, I didn't say it wrong here.
Equals negative E. Negative 1/2.
Nope. So, what's that?
It's not negative.
It's not negative, right? There's no minus sign. E is negative, but so is U. So E is 1/2. I accidentally put a minus sign there. Right? Because E is minus gm1 m2 over 2r. U is minus gm1 m2 over. So E is 1/2. They're both negative, but U is more bigly negative. U is twice as bigly negative as E is the technical description. So E equals minus 2 gm1 is minus gm1 m2 over 2a is 1/2 of the time averaged gravitational potential energy. Or in other words, E is 1/2 time average gravitational potential energy. We put a box around that and we say This is you cannot overemphasize how important it is, the virial theorem. OMG, this is going to be our friend, the virial theorem. This is the virial theorem for the two-body problem. So it's a special case for the two-body problem, but we're about to find out, it's way more general than the two-body problem. So here's the virial theorem for the two-body problem. But we ain't seen nothing yet. More to come. Hold on to your hats. There may be no more important theorem than in all of astrophysics than the virial theorem. Because it just shows up everywhere. It's so powerful. But before we get to all of its glory, let's get a little more two-body glory. Energy conservation. Now allows us to find V as a function of R. In other words, if you know how far apart the two bodies are from one another, you know how fast they're moving. So we can say that minus Gm mu over 2a, right? That's the total energy. We got that expression for the total energy. Well, that's equal to, that's the total energy E. That's equal to, as always, half mu v squared, the kinetic energy of our reduced mass, minus, which is the sum of the kinetic energies of the two actual masses, minus G m mu over R. Cool. We can solve for v squared. V squared, thus, is Gm times 2 over R minus 1 over A. Solve that for v squared. In other words, just take Gmu over R to the other side and then multiply by 2 over mu. The mu's will cancel, and you get Gm times 2 over R minus 1 over A. Or if we like, G times M1 plus M2 times 2 over R minus 1 over A. Boxworthy. So this says, tell me the semi-major axis, tell me the two masses, and I'll tell you how fast they're moving. This is how fast the reduced mass is moving, but remember we've got formulas for V1 and V2 in terms of how fast the reduced mass is moving. You tell me how far apart they are, their masses, and the semi-major axis of orbits. I tell you how fast they're moving. That's what this formula tells us. Break time afterwards. Oh, it's going to be so exciting. I'm going to try Newton's third law. And so it'll be complete. Well, I told you to read the book or the notes to get Kepler's first law. I'm not going to try Newton's third law. Kepler's third law. I hope that's what I said. If I didn't know Kepler's third law. Now, if you drive Newton's third law, you don't drive Newton's third law. That's just a postulate that experiments show is true. We're going to drive Kepler's third law. For the general case, and in the homework, of course, you've been joyfully showing that why when you were in Physics 110, you could get Kepler's third law for circular orbits. So as I was saying, drink in moderation. All right. So, scratchers there. What's that?
They missed all the fun.
They missed all the fun, that's right. They'll tell you all about it. Okay, so anyway. All right, let's derive, oh, I actually did, that's why I said it. I actually put Newton starts law. No, Kepler's third law. All right, note to self, I should probably fix that.
Dr. Carmen,
Yes.
by any chance, were you in a different state when you wrote that?
Here?
Yeah. Do you know what I mean?
Yeah. No, I was in Ohio, and my PA was 0 at the time. I can just tell you that. Yes.
I trust you.
Right. Yes. Okay, so now we can derive Kepler's third law. Exclamation point, this is glorious. Integration of the second law, which is the one that says A dot, the rate at which area is swept out, is L over 2 mu over a full period all the way around the orbit. Gives, well, I integrate from 0 to p dt, this is just a constant, right? L is a constant, mu is a constant, so it's just this times the total time for one revolution. That times p. A equals, I don't know, right there. 0 to p of A dot dt, just to be very explicit in case later I would, equals L over 2 mu, because that's all constant, 0 to p dt, well that's just p. So you just get LP, L over 2 mu times p. The total area of the orbit is L over 2 mu times p. But, take my word for it, wave the chicken feet, right? No, we're not deriving this. The area of an ellipse is pi AB. I mean, you don't derive typically the area of a circle either, you know, but here you can derive this. And I think there is a problem in the book that says derive this formula. You do it by doing the appropriate integral. The area of an ellipse is A equals, well, you can derive the area for a circle from an integral, it's not too hard. A equals pi times the major axis, semi-major axis times the semi-minor axis, which that's very plausible because if it's a circle, how is the semi-major axis related to the radius of the circle?
It's the same.
It's the same. How about the semi-minor axis?
It's the same.
It's the same because for a circle, A and B are the same and they're both equal to the radius. So for a circle, pi r squared. So it's pretty plausible that for an ellipse it's pi a b. We haven't proved it, but it seems believable, right? Because it gives the right formula for a circle. Now there could be some junk on here that would go to 0 as the eccentricity, but there's not. It's just pi a b, what it works out to be. Take my word on it, right? And so, thus, y'all know the waving chicken feet, by the way? You have to explain that to anybody? Is there anybody I've never told about the, have I told you about the waving chicken feet back there? You've never heard, oh, so you talk about a hand wave, you're waving your hands, right? Given my artistic ability, if you want to call it that, I find it difficult to draw realistic hands, unlike, for example, in this show. So I draw chicken feet, and wave those instead. So that's the waving chicken feet. Yes. So, thus, using our formula over there, well, P is 2 mu A over L. So therefore, P squared, we want that because we're going to get P squared is something A cubed, right? P squared, for Kepler's third law, P squared is equal to 4 mu squared, what did I do? The A, capital A. 2 mu capital A over L, because we solved that formula over there. 2 mu capital A over L. So P squared is 4 mu squared over L squared times A squared, which will be pi squared little a squared B squared. P squared is 2 squared mu squared capital A squared over L squared. So that's 4 mu squared pi squared A squared B squared over L squared. But we know that B squared is A squared times 1 minus E squared. So I can say this is A squared times A squared 1 minus E squared because that's what B squared is equal to, times pi, let me put the pi over here. I'll put the pi here. 4 pi squared mu squared A squared 1 minus E squared over, and then we know the formula for the orbital angular momentum, right? That was L is equal to mu times the square root of GM A times 1 minus E squared, right? And that formula for the orbital angular momentum. So square that 2 down on the bottom, that's mu squared times GM, calculate the square root by squaring it, A 1 minus E squared. And now it's time for a cancellation bloodbath. Right? Mu squared, go! 1 minus E squared, go! A squared over A is what?
Wait, A squared
A squared over A is A cubed. P squared's got A cubed over up. Where we're going here. So this is equal to 4 pi squared over G big M A cubed. P squared is 4 pi squared over G big M A cubed. There it is! Newton's form of Kepler's third law. In other words, that K, the constant of proportionality, Kepler just said they're proportional. Newton said, yeah, and the proportionality constant is 4 pi squared over G times the sum of the masses. Newton's form of Kepler's third law. There it is. So notice that, just as an aside, right, the mass of the planet, if we're talking about planets and the sun, right, the mass of the planet is not completely uninvolved, right? So to an awfully good approximation, all that matters is the semi-major axis of the planet's orbit. To an awfully good approximation, its orbital period is independent of mass. But it's only an approximation because this M here in the solar system is the mass of the sun plus the mass of the planet. Anybody know, what is the mass of the sun compared to the mass of Earth, roughly speaking? It's not a million, that's over to one.
It's 9 times, I think.
It's a bit more than that. It's about 300,000 basically times the mass of the Earth, roughly speaking, for the mass of the
I'm
Sun.
thinking volume, never mind.
Oh yeah, volume is more like closer to that, yeah. But for mass, it's about 300,000 times the mass of the Earth. And let's see, so you'll know, so certainly if you put in the Sun and the Earth here, the mass of the Sun plus the mass of the Earth, you ain't missing much if you just call it the mass of the Sun by itself, because the mass of the Earth is so tiny compared to that. What's the most massive planet? Jupiter, right. What's Jupiter's mass compared to Earth's mass?
What?
Correct, it's a lot, yes.
Is it 100 times?
So Saturn's 95 times Earth's mass, so about 100 times Earth's mass. Jupiter is 318 times Earth's mass. So call it 300 times Earth's mass, roughly speaking. But that means, given that the Sun's 300,000 Earth masses, the Sun's mass is 1,000 times the mass of Jupiter. So even with Jupiter, you plug in the mass of the Sun plus the mass of Jupiter, right? You're down to like the third decimal place in terms of the effect that has. So in our solar system, gosh, we can just get away with calling that the mass of the Sun. But if you have two binary stars, well, now all bets are off. They can certainly have masses that are comparable to one another, and so then very much the masses of the two stars are going to both play an important role. But for planets orbiting a star, you can get away with ignoring the mass of the planet in that formula. Unless you're super picky and you want to put it in, and then you can, but that's the point. So in Astronomy 111, we learn p squared is a cubed, and we do a lecture tutorial where they keep asking things like, what would happen if you changed Jupiter and Mercury's places? And then the quick answer is, well, Jupiter would now have Mercury's old period because it's in Mercury's old orbit. Except it's not quite true, because the mass of the Sun plus the mass of Mercury is not quite the same as the mass of the Sun plus the mass of Jupiter. Not quite true, but shut up, right? It doesn't matter. So I do say, so the point is, mass doesn't matter because in p squared equals a cubed, there's no mass there. But I do say, okay, it's a little bit of a lie. Right, so it's an approximation thing, but it's not good. Okay? What questions do you have? Okay? So, note, by the way, in the remember, of course, this is M1 plus M2. So if you're going to stick to SI units, right, this would be the formula to use. You can actually run the numbers if you convert to your time base being Earth years and your distance base being astronomical units, and you re-express G in those units, then you can run the numbers for Earth, and if you make your mass unit the mass of the Sun plus the mass of the Earth, essentially, you run the numbers, and G has a value such that this is equal to 1 in appropriate units, and so p squared is a cubed in those units. But it's kind of fun to show it for yourself, and actually do it in the notes earlier on. This is equal to 1 in units where the masses are in terms of the mass of the Sun plus the mass of the Earth, and which is basically the mass of the Sun, and in terms of the distances are in AU, and in terms of times are in Earth years. It works out to 1. No, I don't do it. I do it right here. I'm not going to do it on the board, but right there in my notes, I put in the actual numbers and show that, in fact, it works out. Okay. Time for gloriosity. The virial theorem, which is again one, it's in the notes, it's in the text, detailed proof here, in which they also basically redefine what is meant by moment of inertia. They define it as the sum of mass times distance of the mass from the origin, but really it's, remember, distance of the mass from the axis of rotation, but they still call it moment of inertia. Anyway, If you're curious and you want to see the proof of this, it starts here, goes through here, and goes all the way down through here. It's not terrible, it's fun to go through, I encourage you to do so, but I don't want to spend class time on it. So I'm just going to state the virial theorem and talk about some of its consequences. And leave it to your own curiosity if you'd like to see the proof of the virial theorem. So, the virial theorem. The astrophysicist's best friend, the virial theorem. Here it is. For a gravitationally bound system in equilibrium, the total energy is 1/2 the time average potential energy. In other words, before when I said, oh, here it is for the two-body problem, it generalizes to any gravitationally bound system in equilibrium, and I'll say what I mean by equilibrium in a minute. The total energy is 1/2 of the time average potential energy. Now really, that we're applying it to gravitationally bound systems, even that's really, it's kind of a special case because what really needs to be true is that the particles interact by central forces that go like 1/r². So it applies in electromagnetism too, except in electromagnetism, charges have this pesky notion that they might want to radiate, and so it's harder to get them in a nice equilibrium. Although that also happens with our gravitationally bound systems too, if you've got charge separations or molecules or whatever. Anyway, it would apply to E and M too, because of the fact that in classical physics, electromagnetism and gravity are mathematically equivalent in terms of they're both central forces that go like 1/r². But what's the big difference between mass and charge? How many kinds of mass are there? One. How many kinds of charge are there? Two. That's the big difference, right? You have plus and minus charge. We don't have plus and minus mass. But other than that, gravity and electromagnetism are the same. So gravity has Gauss's law. You can talk about the total flux of the gravitational acceleration vector through any surface is some number times the total mass enclosed, because it comes from fundamentally the same thing. I said, the proof would be the same because the proof relies on the forces being, or the field vector being an inverse square law force. So, for a gravitationally bound system in equilibrium, the total energy is 1/2 of the time average potential energy. So here, this assumes that we use this convention that U goes to 0 as the separations of the particles go to infinity. That U is 0 and the particles are infinitely far apart from one another. That's the separations of all the particles approaches infinity. So they're all infinitely far away from one another. That's where the potential energy is 0, because that's how we define it for individual pairs of particles. So just make them all infinitely far away from one another, and that's where the potential energy is 0, in a living case, right? If we didn't do that, we'd have to add a constant to this instead of being like that. So it would still apply, you just have to add a constant. Since E equals, we're going to use K to mean the kinetic energy here. You could use T if you wanted to, but we're using K because this is astrophysics. This isn't mechanics, even though we're applying mechanics. So E is K plus U. Let's see, if we time average E Well, the average of the sum is the sum of the averages. So the average, the time average of E is the time average of K plus the time average of U. But wait a minute, what's true about E? Yeah, and so therefore, does it change? So therefore, if I take its average, it's just itself, right? So E is equal to, the total energy is equal to the time average kinetic energy plus the time average potential energy. Since E is a constant. So in other words, we've got different ways to say it. E is the time average kinetic energy plus the time average potential energy. But then the other statement, the statement of zero theory we just said, is that E is half the time average potential energy. So we can say that, yeah, oh here, I should have said, I forgot to do this, colon, and then we say, in other words, like we said before for the two-body problem, E is 1/2 the time average potential energy. So therefore, we can say half the time average potential energy is equal to the time average kinetic energy plus the time average potential energy, which gives us another way to state the virial theory. Here's one way, E is half the time average potential energy. Here's another way, K is equal to minus 1/2 of the time average potential. Just solve for K. K is 1/2 U, 1/2 time average U minus time average U is minus 1/2 time average U. So here's a statement of the virial theorem. Here's another statement of the virial theorem. But wait, how can this be? The kinetic energy can only be positive, so how can it be minus half the time average potential energy? Isn't that a contradiction? How could the kinetic energy be negative? What's the resolution of this apparent dilemma?
Potential energy is negative.
The potential energy is negative, yeah. So minus minus is plus, right? Remember, it's a gravitationally bound system, and that means that its potential energy is negative, and U is negative. So therefore, that K is positive because it's minus a negative quantity, so be sure you understand that. U less than 0, so that time average K is greater than 0. It's okay, we're fine. So let's consider some applications of this. Some truly profound applications of all this. So for it to apply and to be in equilibrium, what we basically mean, true equilibrium means it's not changing at all over time in its statistical properties, in its average properties, if you will. And you have to come up with a precise definition of that. But as you'll see, we learned by look at specific examples. That it's gravitationally bound means it can't be a system that's flying apart. It could not be some cloud that's expanding and just going to expand forever. That's not a bound system. So it's got to be a bound system. The particles' overall potential energy is negative, overall energy is negative. So you could have a bunch of stars in, say, a globular cluster. It's bound, meaning none of the stars are flying away. They're just going around their complicated orbits, and sure, the details are changing, but on the other hand, it's a bound system. Nobody's flying away from anybody else, kind of the idea there. So let's look at a good example of applying this. Applications. Consider an interstellar cloud collapsing to form a protostar. That's how stars form. big clouds of interstellar gas and dust get into a condition where their gravity is dominating over their internal pressure so that the star can collapse. The cloud can collapse and eventually form a protostar. Consider an interstellar cloud collapsing to form a protostar. So you might object, wait a minute, it's not in equilibrium then, it's shrinking over time. But if it's doing so slowly, it's in quasi-equilibrium, and we still get to apply the virial theorem in that situation. As long as the time scale over which it's changing is very large, we can say it's in a quasi-equilibrium state, and it's okay to apply the virial theorem to it. Trust me on this. Consider an interstellar cloud collapsing to form a protostar. Slowly collapsing to form a protostar. It can take millions of years to finish that process. Slowly collapsing to form a protostar. If the collapse is slow, the cloud is in quasi-equilibrium. By quasi means almost. The cloud is in quasi-equilibrium. And we get to use the virial theorem. Because it's close enough. It starts out very large and very cold. The cloud that formed the sun started out like about a light year across. Much bigger than the sun is now, for sure. Very large. About a light year across. And very cold. Turns out, just a few Kelvin above absolute zero. So, the atoms are very far apart. So what does that suggest about the gravitational potential energy if the atoms that are pulling on one another gravitationally, if they're very far apart from one another, what does that say about the gravitational potential energy? It's roughly, remember we said, what happens to you is everything gets very far apart from one another. It's nearly zero. It's almost zero. So U starts out as approximately zero. You know how fast molecules in this room are moving due to being at around room temperature or so? You might revise that. They're actually moving thousands of miles an hour. If you calculate the molecular speeds for room temperatures, it's several thousand miles an hour. So the air molecules in here are constantly smacking into one another. The mean free path is quite short. Or I should say that's not, well, it is because they're pretty crowded, but the time between collisions is very, very tiny because they're moving thousands of miles an hour and they're, microscopically far apart from one another. So they're constantly banging into one another. So they have kinetic energy because they're banging around, right? They're moving, right? They have kinetic energy. So think about that. You got a car, right? and it's driving down the road at 60 miles an hour. And we like to say, okay, what's its kinetic energy? Well, it's 1/2 mv squared, where you turn 60 miles an hour into meters per second if you want SI, plug it in, you get some number of joules out. That's its bulk kinetic energy. But how about its kinetic energy due to all those random thermal motions of its atoms and molecules? They're moving a lot faster than 60 miles an hour. They're moving, do the numbers for yourself, right? You calculate, they're moving thousands of miles an hour. So the thermal kinetic energy of a car driving down the highway is vastly larger than its bulk kinetic energy. In other words, it's thermal energy, but that's really kinetic energy. It's just random motions. That dominates the total, what we would call K for that system, because it's every kind of kinetic energy, including the thermal kinetic energy of all the jiggling around. So fun fact, right? Most of the kinetic energy of a car is thermal kinetic energy. It's vastly larger than its kinetic energy due to bulk motions, because it's equivalent to a car going thousands of miles an hour. Its thermal kinetic energy is equivalent to its bulk kinetic energy, whereas if it was going thousands of miles an hour. Same deal for you, right? Your thermal kinetic energy of your atoms and molecules jiggling around, that's equivalent to your kinetic energy in bulk if you were going thousands of miles an hour. So most of your kinetic energy is thermal kinetic energy. We just usually don't count it because we're kind of often more interested in translational motion as a whole of the center of mass, but it's true. All that's to say, K represents primarily the random thermal kinetic energy of the cloud's particles. The random thermal KE of the cloud's particles, its atoms and molecules, and maybe free electrons once it gets high enough. In other words, when we apply the virial theorem, often what we mean by K is the thermal kinetic energy related to its temperature. That's because it applies to any kind of kinetic energy. And when we apply it to like interstellar clouds, that sort of thing, we typically, K is really referring to thermal kinetic energy. The cloud is cold, it's all shivery, it's a few Kelvin. So to start, what can we approximate its K as? Also zero, because it's very cold. It's very cold, so it don't got much thermal kinetic energy equals zero. So the cloud's initial total energy is E equals K plus U equals 0. It starts out with essentially zero energy. Large and cold means zero energy. Now consider when the cloud has shrunk down to some radius r that's much smaller than its initial size. I heard that. So it's shrunk down to some radius r. I heard that. So here's our cloud, its mass m, its radius r. We want an estimate for its internal gravitational potential energy, which would really be the sum of all the g m1, m2s over r inside the cloud. So if I really wanted to write it, it would be the sum over I doesn't equals j. Well, actually, I should say for I greater than j of minus g mij over rij, where, in other words, here's two particles, here's particle I, here's particle j. The distance between them is, we'll call that rij. The gravitational potential energy is minus g, the product of their masses divided by their distance. So we add up all the minus g mij's over rij's, and I say for I greater than j, because 1, you don't want I to equal j, you don't want to call it like there's a self-energy for the particles, it has to be for other particles. 2, I has to be greater than j, or you could also make it j greater than I, because you don't want to double count. You don't want to include both M66, M94 over R6694 and M94, M66 over R9466, because that's the same thing. That's the same two particles. So we say I is greater than J, or you could make it 1/2 the sum over I not J, and the 1/2 would take account of the double counting. You may do something like that in E and M, talking about the electrostatic potential energy of a set of point charges. It's a very similar thing. It's mathematically the same. Having said all that, we ain't going to try to actually evaluate that. It would depend in detail on where other particles are, or if you consider it continuous, you've got density as a function of position. You could do an integral to figure out what this is, but we can get an estimate of what it is. This is a dimensional analysis estimate, we call it, which won't be quite right, but it'll only be off by some number that is of order 1. And this is a very common thing to do, and it's a skill to develop. So tell me, I need an expression for u, and if I have two particles, u is g, mass of the first particle, mass of the second particle over the distance between them, what do I have to construct a formula for the gravitational potential energy of that cloud? I have capital M and I have R. Those are the two biggest characteristics of the cloud. What can I create, what formula can I create that has mass squared in it, and 1 times m2 is units of mass squared, kilograms squared. What could I make for a formula, minus g, what could I get to make something that has the same units of m1, m2, using capital M and R as my ingredients? What could I use?
If the masses of two bodies are same, you can have that as m squared.
Sure. Here we've got gazillions of particles. This is a single body made of many, many particles. Or I can even imagine it's, there's nothing like this in nature per se, but it's a continuous fluid of mass. There's mass everywhere. It's got a continuous density distribution. So you're on the right track. What can I construct that has units of mass squared using M and R? Do I need both of them? How can I construct something that has units of kilograms squared in the numerator? I want something in the numerator that has units of kilograms squared. Here's my ingredients. The mass of the cloud and its radius. Yes?
Could you do negative g capital M squared over r?
That's exactly what we're going to do, yeah. I get the units right if I say minus g capital M squared over capital R. Does this not have exactly the same unit? Does this not have gravitational potential energy units? Right? Minus gm squared over r has gravitational potential energy units. I said it's approximate. If I give you, and you're going to get problems that deal with this, if you have a density distribution, say as a function of radius, you can do an integral to get the exact result, and the answer will be minus some number times gm squared over r, and that number will be something like 5/3, or 2/5, or 4/7. It's still going to depend on what the exact density distribution is, but it's not going to be a quadrillion, and it's not going to be, 0.00006 or something like that. It'll be a a number which isn't that different from 1, is what it comes down to. So you'll see an example of that. So this is our approximation for the cloud's gravitational potential energy. It's minus gm squared over r. That'll be about right for its gravitational potential energy. Okay? You're reasonably buying what I'm saying. I know this is going to be a little bit, the first time you see it, get used to it. This kind of thing is, theoreticians do this sort of thing all the time, where you have something that would be difficult, and even non-theoreticians, you have something that would be difficult to compute exactly, but can I do a hand waving, chicken feet waving, back of the envelope estimate of what it ought to be? There it is. There it is. Minus gm squared over r has the right units. It's about right. So that's the gravitational potential energy. It's been collapsing in quantity equilibrium, so we get to apply the virial theorem here. It's collapsing very slowly, so at this time we can say the virial theorem applies for any radius, as long as this collapse is slow, by the virial theorem. The internal KE, the internal thermal KE, because the virial theorem applies to all kinetic energy, including thermal kinetic energy. The internal thermal kinetic energy is now minus 1/2 times the gravitational potential energy. But wait a minute. When the cloud started out, those were both 0, but now it has some negative gravitational potential energy. So the virial theorem says it now has some positive internal thermokinetic energy. In other words, the cloud is hot. The cloud is hot now. The cloud is hot. What questions do you have? Because trust me, I'm going to make you go through this argument on an exam or something similar to it. It's because I really want you to understand it. It's so fundamental. The cloud is hot. The total energy, is the total energy 0 like it started? Is it positive now, or is it negative now? Now the kinetic energy is minus 1/2 the gravitational potential energy. If the energy were 0, those would both have to be equal and opposite, but they're not. So the energy is not 0 anymore like it started. So the positive thermokinetic energy is half as big as the negative gravitational potential energy. So who wins? Is the total energy positive or negative?
Negative.
It's negative, right? Because the positive KE is only half as big as the negative PE. So the total energy is now negative. Total energy is now negative. It's a bound system. It's got to be. The total energy is now negative. It's got more gravitational potential energy than it does thermokinetic energy, whereas before they were both 0. So the total energy is now negative instead of 0. Started out as 0, now it's negative. So the star has lost energy. The cloud has lost energy. It started out at 0 energy. Now the cloud has some negative energy value, which is less energy than 0. The cloud has lost energy. In collapsing, the cloud has lost energy. How much? Well, its energy is now minus gm squared over 2r roughly. So it's lost that energy. GM squared over 2R, it's lost that much energy. The cloud has, and this is the kind of thing, right, because there's pluses and minuses here, it can be like, wait, what? So think about this carefully on your own time. The cloud has lost energy equal to the absolute value of half of its potential energy. That's how much energy is lost. So it now has that negative value of energy compared to 0 before, since starting to collapse. The cloud has lost energy equal to half its current potential energy. In other words, it's lost an energy of approximately, and this is an approximate, but the essentially exact result is half the PE. With our approximation, it's lost energy equal to Gn squared over 2R since it started to collapse. So you can put in numbers. You could say, okay, if it's the mass of the sun, and we get to the point where it was twice the sun's current radius, you could put in those numbers and figure out how much energy it's lost since it started collapsing. Where did it go? Where did it go? Because does energy just disappear from the universe? Well, the answer is yes. When we get to cosmology, we'll see it does. But for our system here, that's not applicable. Where did that energy go? The universe is losing energy as it expands because cosmic microwave background photons are stretching, which makes their wavelength longer, which makes their energy smaller. They're all losing energy. Where's it going? Nowhere. It's just disappearing. Energy is not conserved by the universe as a whole. But that's not the case for our cloud here. We get to use energy conservation. So we started out with 0 energy. The cloud has lost that much potential energy there. Where did it go? So some of the gravitational energy lost has heated up the cloud. That's absolutely right. Where did the rest of it go? What do you think? No. Turns out no, because it had. That's not the main thing. It would have had maybe a slight rotation before. If it's true it had no angular momentum, it still doesn't have any angular momentum. So that's not it. How are you dissipating energy right now? You ate food, right? And you're metabolizing that food. Does that energy all stay inside your body, or does it go somewhere? Yeah, how? You're sitting there doing what right now? You're radiating. Yeah, you're giving off infrared radiation. If we had a thermal camera, it'd be like, oh, you are positively aglow. So is our protostellar cloud. It's glowing. It's giving off infrared radiation. It's radiating. So, in other words, since energy is conserved, if the cloud lost that much energy, that energy got turned into thermal radiation, infrared radiation for the most part. Since energy is conserved, bonus time, I'm giving you some little extra quality education. That clock's a little fast, it's only 2 minutes so far. Since energy is conserved, we conclude the following. And all we needed was the virial theory. We didn't need to do huge detailed calculations. We conclude that half the gravitational potential energy released in the contraction gravitational PE released in the contraction goes into heating up the star, that piece over there. Half of it went into heating up that cloud, that future star, because in fact its thermal energy is equal to minus half its gravitational potential energy. And the other half, it's a 50-50 mix. and the other half is radiated away. As mostly infrared radiation. And in fact, protostars are gravity powered. Protostars' power source is gravitational contraction. That's how they're powered. And in fact, when the sun was a protostar, it was much more luminous than it is now. That gravity power was giving off much more radiation than the sun is now that it's nuclear powered. When the sun was a protostar, it was vastly more luminous than it is now, but it was mostly infrared radiation because it was much bigger and cooler than it is now. As the cloud collapses, eventually, so it keeps heating up, keeps heating up, keeps heating up, eventually the core reaches the ignition point for nuclear fusion of hydrogen and helium, and now you've got this energy source that can counteract the contraction, and we have a star is born. It becomes a ZANS star, a zero-age main sequence star, at which point it spends a long time fusing hydrogen and helium in its core, and so we'll certainly tell more of that story later, but the fascinating thing is from the virial theorem we can say it's a 50-50 mix. Half the gravitational potential energy heats up the star, half of it is radiating away. Ooh. Cool.